Next up, we have Kevin 2, who's going to be talking about how to distribute your places all over the place.
First, I'd like to talk quickly about places. Places allows you to spawn multiple parallel execution units all within a single operating system process. So you kind of have, you can think of like mini Racket VMs, but all living inside one Racket process. And of course, places have channels. So all these places can communicate messages back and forth in between each other. And if we look at what places looks like in code, we see that we have a function that will be executed in newly created places that takes an initial argument, which is the channel to communicate with its creator. And then the body of the program has a section which actually creates a new place, and then it communicates with that place. So this is places. But what we'd like to do is to take our places and distribute them across machines that are running over a network. And we like those places to be able to communicate over place channels, even though they're not on the same machine, even though they're not in the same process. We want them to transparently be able to communicate as if they were. And if you so choose, you can spawn multiple places within each Racket process on each one of these machines. This is what we call distributed places. Distributed places is not a pile of functions, and it's not an FFI wraparound an external library like MPI, for example. It's a language extension. And as we've seen today, language extensions in Racket are easy to do. So I'd like to show you quickly how easy it is to take the places program we just had and turn it into a distributed places program. We have this new create place node function, and we specify a machine that we want the new Racket process to be spawned on. And then when we create the place, we add this additional argument at that tells us where to spawn the new place. If there is no at argument, then the place is spawned on the current Racket process. If we specified a node, then the new place will be spawned wherever that node lies. So now we'll quickly take a closer look at the distributed places API. I mentioned the create place node that takes a host name. It takes a bunch of optional arguments. You can specify a port, so you can actually run two Racket processes on the same machine at different ports. If your Racket executable or the SSH binaries in this custom location, you can specify those. And you can do some other more advanced features, such as specifying whether I/O should be sent to logging infrastructure or to reuse the current ports. Now, dynamic place is a call that originates with the original places work. And all we've done is we've augmented it with two named arguments. The at argument specifies the node to remotely launch this dynamic place on. And we also allow dynamic places to be named. If a dynamic place is not named, it's essentially anonymous. Only its creator can communicate with it. But if you name the place, then other people can connect to that node and connect to the place and communicate with it. So to implement distributed places, we had to support spawning remote processes. And we reused Racket's excellent exec functionality to do this. We essentially exec an SSH process that launches Racket remotely. So you don't have to run around all machines and start Racket. Your Racket program can do that for you on these remote machines, assuming you have SSH with your keys distributed and set up. The second part we had to do is we had to allow for place messages to be sent across sockets. And this happens transparently. You don't have to open a socket. You don't have to do any socket programming. You just say, send this message to this place. And we intercept calls that are going to be remote, send them over the TCP socket, and handle all the networking work for you. And the last thing we did, which you can't read, is that we integrated with Racket's concurrency primitives. And what this basically means is that distributed places and distributed place channels can be placed inside the sync call. And you can wait for events to occur on those things just as you can with other event objects such as files and network ports and things like that. So in finishing up, I'd like to, yeah, you have a question?
Does the TCP connection get transmitted over the SSH connection, or is that in the clear?
It's in the clear. Yeah, so there's lots of reasons for that, but it's not embedded in the SSH connection. So we assume a trusted environment here.
Okay.
We assume kind of like a cluster environment. So I'd like to just quickly show some higher level distributed frameworks that we've built, simple ones. You've all seen these before, but we've built them on top of distributed places. The first one is an RPC server, which this one is a tuple server that basically just wraps a hash. But we're able to connect to the remote node and set things into the tuple server and then get them back. So the basic RPC functionality. We can also build simple MPI on top of distributed places. So here's your node list. That's very familiar from MPI. You have an MPI init. You have some collective communication operations, such as all reduce and MPI finish. That's all I really want you to see from this. And then last is map reduce. You can write mappers and reducers and outputter functions and call map reduce on this. If you specify, the list of worker nodes that you've created with distributed places, or actually, if you give it a list of worker nodes, it'll create the distributed places and implement MapReduce for you. So the conclusions is that language extension, the ability to take Racket and add places and then add distributed places to extend these languages makes the use of distributed programming concise, both in the implementation and in the use of it. Second, we were able to reuse places as API, specifically dynamic place and place channels to implement distributed places. And then these distributed places constructs serve as a foundation for building higher level APIs, distributed APIs such as MapReduce, MPI, RPC, things like that. And we hope that this can be a roadmap for dynamic language implementers to be able to add parallelism and distributed parallelism to existing virtual machines. And that's it. Thank you.